Before we dig into an example, we will do so in just a moment, let's provide an interpretation of what's going on here. What does this surface integral thing mean? So let's relate it back to something that we saw earlier. So just like, here's the interpretation. So just like the line integral over a curve C of f of x comma y d lowercase s adds up z values along a curve. So for instance, you have in the xy plane, you have a curve somewhere. Okay, and so, maybe you travel this way along some curve. Okay, starting maybe here, ending there, and really what this integral right here is trying to pick up is it's just trying to go through and at each point along the way just get the value of f of x comma y at each spot. I mean, not just at the dots that I'm drawing, but literally every point on here, and then just add those up. That's what this integral would be doing. And in the same way, the double integral over s of a function f of x comma y comma z d, now capital S, this adds up, I guess we'll call them w values of a function, whose output variable we'll call w right now, w of f of x comma y comma z. So we're just adding up outputs of a function, of a given function f, just like we were earlier, for points. Instead of along a curve, now it's just for points that are in the surface. So it's weird to say along a surface. Along a curve, you just travel in the direction you're given. So we'll just say for points x, y, z in the surface. So what I'm trying to say is, if you have in three-dimensional space, you have a surface here. Maybe it doesn't have to, it can bend funny or whatever. It just imagine that you threw a towel in glue, and then you can kind of move a towel around, and at some point it's going to freeze in its actual shape. So you have this surface here, capital S. And so just like a moment ago, we were saying, oh, we would take each point along the curve and find out what the output of f is. Same deal here. It's each point in the surface, whether it's on the boundary or somewhere in the inside, we would just be adding up the outputs of this function f, or the w values. Now let's take a look at an actual example. All right, so let's do the following. Let's integrate the function f of x comma y comma z equals the fraction y over xz plus 8x squared over the surface capital S, which will be given by a drawing. So here's how we'll describe the surface. Okay, x-axis, y-axis, z-axis. We're going to have a cone that looks like this. Okay, so there's a surface. We'll shade sort of the inside part of this cone here. It looks like a megaphone. This angle this way will be 45 degrees. Okay, so we will need to parameterize the surface. Yeah, and S is parameterized by, here's one option anyway. So R of u comma v is equal to u, so x coordinates just u, and then the x value, or now u value, also happens to be the radius of the circle we need, so we can go with u cosine v, comma u, let's fix how that's written here, u cosine of v, comma u sine of v. Sine of v. Okay, there's a parameterization with parameter domain. Well, looks like, oh, sorry, I forgot to put into the picture here where this ends. Sorry, this is a little messy, but the ending here is at x is 10. Okay, so then the parameter domain capital D is described this way. It's so u should be going from 0 to 10, and then v should be going from 0 to 2 pi. So we can take the parameterization and compute the partial derivative with respect to u and partial derivative with respect to v. These are things we would have done in the previous section as well. So 1 comma cosine of v comma sine of v, and then for r sub v differentiating with respect to v, we'll have 0 comma negative u sine of v comma u cosine of v, and we will skip the hand calculation of the cross product. You should go and check, but when you do so, you will get here u comma negative u cosine of v comma negative u sine of v. And then when we take the magnitude of this, right, because look, we're just trying to get all the pieces that appear there. So when we compute the magnitude, again, this would have been something we would have done last section of just finding the surface area. Okay, the magnitude ends up being, in summary, root u squared plus u squared, which ends up being absolute value of u times root 2, keeping in mind that actually in our example u is greater than or equal to 0. I mean, u is always stuck between 0 and 10, so the absolute value of u simplifies to u. We'll have u times root 2 here. So then what's ds? So, looking back up here, ds was supposed to be that cross product, magnitude of cross product, times dA. So in our example, then, we'll have that capital DS. So from here, we'll say that d capital S is equal to this thing that we just computed. So u root 2 times dA, where dA is later going to get replaced with du dv or dv du or polar if we want to do something like that. Let's get there when we get there. The next thing we need is we're going to need this f of r of u comma v. Yeah, so f of r of u comma v. Now this is a little funky because to feed into f, you're supposed to feed in 3 separate real numbers, and this composition's a little odd, but in the same way that we had seen things like this before, this really just in terms of implementation just means, and even saying composing here is a little strange, but f of x of u comma v comma y of u comma v comma z of u comma v. And let's work that out here. This is going to be, well, we had a y up here, so that y needs to get replaced with u cosine of v. So u cosine of v. And then in the denominator, we had x times z, so that'll be u times u sine of v. Right, so u times u sine of v. Then there's a plus sign here that we just copied. Now we have an 8 to copy, and then it says x squared here, so we're going to have u squared. Something that looks like that. Now let's just clean up a little bit. What we have involved here is, you'll notice that there's actually, we can factor in the denominator a u out, we can cancel a u on top and bottom, then we'll be left with cosine of v over u sine of v plus 8u. So now let's go ahead and set up the integral we need. So the double integral over s of f of x comma y comma z ds is equal to, let me just, sorry, it's at the top of the page. Let me just copy paste this down here so that it's easier in terms of reference for what we're doing. Okay, and then we'll replace the pieces here. Yeah, so let's not worry about the capital D and the DA yet. So usually it's kind of nice to set up a lot of other things first. in terms of cleaning things up. So we'll just have double integral over d, and then this f of r of u comma v, we had just simplified to this fraction, so let's go ahead and make that replacement. Cosine of v over u sine of v plus 8u. Okay, that takes care of that part. Now we need the magnitude of the cross product, which we had computed right here, was u root 2, and then we just should copy down dA here. Okay, again, this entire part, u root 2 times dA, that's what ds is, yeah? So maybe I'll circle those in a new color here. Let's do this. So the ds, that was right here, right there, turned into u root 2 dA. Well, now what? There's actually, this is actually a fairly nice integral to do. So let's do a couple things. Let's leave a little bit of space between these two integral signs, because we'll go ahead and replace the dA with a du dv or a dv du. But you'll notice also that this u is going to cancel with those u's, right? Just in terms of doing a factoring in the denominator and so on. Okay, so we should, at least for what we need to integrate. Oh, let's also, while we're doing this, let's take this root 2 and bring it in front of the integral. So root 2 times integral sign, leave a little more space, integral sign, and then we'll have cosine of v over, okay, the u here cancels with the u's there, so the denominator will be left with sine of v plus 8. Let's go ahead and write this as a du dv integral. We don't need to actually work much harder. Sometimes, based on the shape you have, we might have been thinking polar coordinates or something like that. But actually, remember, we're actually integrating over d, and our parameter domain. We did the hard work in with the parameterization. The parameter domain is right here. If we draw on the UV plane, we're talking about just a rectangle. So this should just be u going from 0 to 10 and v going from 0 to 2 pi. Okay, so this is actually a really nice integral to do. We won't do all the details. Let me just point out that this should become, in the end, let's see. Well, integrating with respect to u is not going to do anything. Yeah, because there's actually no u's in the integrand anymore. So when you integrate, you just stick on a u and then evaluate u at 10 and at 0. So in the end, I hope you'll, without going through all the details of that integral, you can go through it. You'll have a 10 root 2 times integral from 0 to 2 pi of, just with respect to v, cosine of v over sine of v plus 8. Now this integral you can really give to just somebody taking Calc 1, really, right? So you're going to need to do a substitution. Let's not call it a u substitution. It's just, there's already a u floating around. So how about we call it a p substitution? P is equal to 8 plus sine of v will do it. We will not go through the details here. If all works out, well, it was maybe not that exciting that the integral here should evaluate to 0. But the point wasn't really about getting this final number. I just wanted to illustrate that you could. I hope it's clear to y'all that the point was to take this and, based on what the implementation looks like, turn it into that and then really turn it into that.